Hey, what's going on? So we're going to return to the problem of the very first couple of episodes of this series. And we're going to be concerned with the finite elements, if you will, or finite, different. Basically, we're focusing on a Poisson equation, right, that's encoding an equilibrium. And here's the domain. And we're going to instead treat this as a nested domain. So this would be like a subset of 2h, which would be a subset of, I guess 4h, we'll double it, up until we have that whatever here is a subset of some full, like capital H. And this corresponds to, again, stiffness matrices, but they would also, be listed and associated with those particular scales. Same with the solution spaces. All right, and these would typically be solved with Galerkin methods. All right, and we can consider the linear system. And so as you can see, this is starting to get kind of big, but we're going to consider this particular Galerkin solution. All right, that looks like this. And what's going to happen is on a finer grid, you can think of these as like many little small springs. We'll get fine details or high frequencies in the number, in the error, right? And the error components in these really small frequencies, after a few relaxations, will actually become pretty smooth. So you can think about this like, So if you remember from the stability analysis and when we were talking about how numerical schemes kind of smooth things out versus like or diffusion type problem or elliptic operators specifically do this. That is because of the averaging that's happening in the grid and in the finite difference schemes. So the long wavelength imbalances will kind of like, or the neighboring nodes will move together, but long wavelength balances will persist. And so physically, you can think about this, again, if I had like some full H, right, and then I'm discretizing it, and then it doubles, right, and so on, right, where this is H. The low frequency errors, they're going to look something like this. So if I were to plot this, it would look something like this. And here it would be kind of noisy. And it's a superposition, really, it's a superposition of both the low frequency waves and the kind of more, it would be more high frequency noise that looks like that, okay? And that's really essentially what we would call the error at the really fine grid here. All right, and physically, these are like little kinks or wrinkles in the membrane. You can think of it as like a membrane. It's easy to relax locally, if we evolve it, because the system will smooth everything out over time. But the low frequency errors are more gentle. And they're like sags or tilts, if you will, that averaging, we'll barely notice them. And almost, no local force imbalance will happen between them. So the multi-grid approach that we're doing is going to try to exploit this, all right, this scale separation. And it's scale separation in physics allows us to define, more local physics that's like smoothing and fixing small scale wrinkles quickly, and then global physics that happens, on course, solving, fixes large scale shapes very computationally cheaply. All right, so that's the whole goal of what we're doing here. All right, and so what this looks like is we can consider something called the Jacobi iteration, right? and how we can think about this. And this is really the simplest way to smooth something. So for a one-dimensional Poisson operator, this usually looks like a tridiagonal matrix with 2 on the diagonal and -1 and off diagonals and scaled by some. So we just have like some scaling of 1 over h. All right. And what's happening is we can have some u sub j. We're going to use the same notation that we did for a previous episode. And except we're using im here instead of in. And im just represents like the smoothing. All right, so we have a finite difference scheme. We've seen this before, but we're going to add an h parameter that's basically going to be our smoothing kind of parameter. It's going to control the level at which we're smoothing. What we can do is apply von Neumann analysis. And so as you can see, we're really kind of bringing everything together from all of our episodes, so it's really important that you followed along. But you have the Fourier mode here, which will be given in terms of some z, and the coefficients in terms of the m that are describing our smoothing, some I j k h, right? Same thing that we did previously. And of course, remember this c sub k, the coefficients can be in terms of some cosine here. And the amplification factor, this amplification factor is going to have a magnitude of the absolute value of cosine kh, all right, where h is that scaling parameter. And the amplification, really, we're going to be able to classify frequencies with this. Because near the Niskett limit, if you remember how we defined this, whenever this equals pi, if you just plug it into the amplification factor, the cosine of pi is -1, right? So, when kh equals pi, this becomes -1, all right? But after one relaxation step, the mode is eliminated in the high frequency. This is again high. This is a high frequency limit, okay? And each effective factor is eliminated for the error because the residual projection is effectively damping it very strongly. And so what would happen here is this component, this high frequency, let's say this is high frequency and low frequency. This high frequency component will just look flat, right? But it'll retain the original smoothness of the error that we were looking at, all right? And so technically, after smoothing with some Jacobi iteration, this is what's happening via von Neumann analysis. The lower frequencies, what does that look like? Well, that would be when kh is much less than 1, all right? Which would imply, if this is much less than 1, right? This cosine is much less than 1, but we're only looking at the absolute value. So we'll be just concerned with the fact that, cosine, cosine of let's think about this. So if it's much less than -1, then we can have that it's approximately 1 minus from the Taylor expansion, which is just approximately 1, okay? Because this part goes to 0. Sorry, I had to think about that for a second. Yeah, so the error reduction here per step, so the error reduction is approximately 0, all right? So the low modes, again, like they're unnoticed, they're untouched. It's just the high frequency part that is getting smoothed out. All right, and maybe we should talk a little bit more about the high frequency part, because the smoothing rate, right? It's really a reduction again of that error, of the high frequency error, and it basically tells us that we want to find the maximum kh on the interval of pi over 2 to pi, right? Because it's an absolute value. And of course, this is for the magnitude of cosine kh. We want the maximum argument, and of course that gives us the cosine of pi over 2, which is 0. So again, this implies that high modes are damped by factor 0 in like 1 to 2 steps, right? So that's kind of a smoothing rule in general, and a few relaxation steps are there, and there's different ways that we can actually smooth. We're not going to get super specific, but for damped, there's Jacobi. So I'll just list them out. You can look these up, but there's damped Jacobi. There's also another one that's really interesting. It's called the Gauss Seidel, and this is like more of an asymmetric damping. All right, but the principle will hold, 1 to 3 relaxation steps. It'll eliminate most of the high frequency error, while the low frequencies will be barely, recovered, or barely touched. So this one's just more asymmetric, but I mean they still kind of do the same thing. It just depends on, what your tastes are and what specific problems you might be using or might be trying to solve. But yeah, in conclusion, really, the oscillatory, we're effectively eliminating the oscillatory behavior of the error for very fine grids, and leave that smooth low frequency components almost unchanged, and we can leverage that. That's going to allow us to make the computational complexity a little bit, it's going to make it a little bit less, crazy or crazy hard and complicated, right? So what we can do is try to do something called coarse grid correction, and this is targeted specifically at smooth errors. So we can say let U tilde of H be the iterate after smoothing. All right, so we smoothed out the grid very nicely. The algebraic error, if we just want to define the error, then it would just be defined as U of the original Galerkin solution minus U tilde, right? After we iterated and smoothed out, throughout the scales. And so what we can do is come up with an idea, right? And instead of continuously, continuing to smooth the fine grid, right? This is inefficient for smooth error, right? So we can actually restrict the residual to a coarser grid, right? Whatever residual that we have, and then we calculate to solve it on a smaller coarse grid, or the same problem, approximately, and then interpolate the course correction in an interesting way. And when we interpolate it back to the fine grid, this then allows us to solve it in a particular way. So again, so the whole idea was just, what is the residual between, f sub h that's defined by this particular solution that we have that's smoothed, right? And this should be equivalent to, A in the total error, right? For the true one. And, what we're doing here is saying we're going to apply a series of steps, right? So, one, what we can do is pre-smooth, right? So apply V1 relaxation steps, all right? So, and this would be applied to U tilde, from 0 to get the smoothed U after some series of smoothing in the coarser or in the fine grid, all right? Smoothing out those high frequency errors. And then what we can do is compute the residual that we defined up here, all right, which will look like this. And then we can restrict the residual, right, to a coarser grid, right? So coursing it out and applying some restriction operator. And this is called a restriction operator, which basically is essentially trying to do a full, weighting or injection, if you will, of the residual here that we originally got onto the coarser grid, right? And then what we can do is solve the coarse grid equation exactly, all right, for the error that's true to that grid there, which will be equal to our H. 5. We can then it's called prolong, but it's really just kind of interpolate, if you will. You have two different data points, and what you can do is interpolate a correction, right? So let's say the error correction. It's not correlation; it's correction. With our restriction operator again. I'm missing that. Right. So restricting again, from we're trying to get the original correction from, to H. All right, going back down to the grid, and this is usually this is a kind of bilinear interpolation that's done. And then what you'll do is correct fine grid iterate, right? And what this looks like is just saying here's the smooth solution, and here's the plus the error that we kind of got on from correcting the grid. And then we will finally post smooth. So we'll apply, we'll apply V sub 2 more relaxation steps. Okay. Now, what this allows us to do then is think about. So let's first kind of draw this out. I think drawing it out will help a little bit. So, if we want to, let's define that, like, hey, let's say this is H here, and let's say this is 2H. All right, and you can think about let's look at the graph here. The graph on E sub H is going to simply, it's going to be a smoother error on kind of on a fine grid, right? We smoothed it out, but the same error let's say we have E 2H. This is going to be a coarser grid. What's going to happen is, it's going to be rougher, right? And what we're going to have to do is the reason why it's rougher is because we're restricting and we're injecting this finer grid, we're injecting this finer grid onto the coarser grid, and now it's rough relative to the coarser grid, and we can actually solve this efficiently. All right, by means of the step that we outlined here. All right, by just simply restricting and then interpolating the error correction that needs to be made. Okay. Now, what we then have is we're going to arrive at a mathematical theorem that is pretty important. This is called multigrid convergence. All right, and this is a classical result, but the smoother curve, if you will, has smoothing properties. So it's damping those high modes by a factor. So we'll say P sub s is less than 1. And it's independent of how coarse the grid is, right? The smoothing property is independent of this, and we're damping the high note. We're damping the higher frequencies. Now, another thing that's important to note is the coarse grid correction itself, which looks like the stiffness matrix, should be the interpolation and the restriction and the prolongation, right? This should be consistent, right? This is called a Galerkin. The projection itself is a or that coarse grid correction itself is a Galerkin Galerkin coarse operator. That's what that means. There's a coarseness, or there's an orthogonality within the interpolation and prolongation, or prolongation and restriction. All right, so that we can get that error term. All right, this is assumed because we spent a really long time proving Galerkin orthogonality. And again, this prolongation here. So we're going from 2h to h, right, to the finer grid, and the restriction. So this is prolongation, and then here's restriction. These satisfy approximation properties. So that just means like that would mean that the prolongation is accurate to order of h squared. So it's accurate to the order of which the grid is self squared is, if that makes any sense. That's the complexity. That's the computational complexity that's required for how accurate we are. And I'm not going to go through and prove that. That's not really what I'm interested in. If you're kind of a nerd, you can look this stuff up, but I just want to leave this out. This is more intuitive, right? This is a machine mathematics series, but ultimately we're more focused on getting the intuition to build things with. Okay, so by no means is this like beginner stuff, but it is really important to talk about these things from a higher level and not be super concerned with like the nitty-gritty formalism, right? But and like forgetting exactly what we're talking about. Okay, which is we're trying to solve Poisson's equation over multiple coarse-grained subsets of the same domain. All right, now, and of course we have this mechanism of restriction and prolongation that's allowing us to have their own approximation properties, right, and complexity associated with them. Okay, so there's something called the two-level iteration operator, and this is said to be something called a V cycle, right? And I'll draw this out, but this m sub h, this norm of m sub h is going to be called a two-level iteration operator, and it'll be less than or equal to some rho, right? That's less than 1. And the important thing to note is that the parameter rho is independent of h, of our coarse graining. So typical values of rho, is approximately like around this area for standard bilinear elements, and a full weighting, 1 to 2, basically like after 1 to 2 like smoothings or whatever, error reduction. We usually get like error reduction by 3 to 10 times per V cycle. That's kind of insane. And this is independent of mesh size as well. So it doesn't matter how big the mesh size actually is. We really get a true sense of mesh independence because of the scale, the scaling that we're able to do. All right, so that's pretty powerful. And we can, again, in order to prove such a thing, right? How do we prove that if we have these properties, we will get this? Well, it involves a couple of things, but typically what you would want to do in a little proof sketch is if you took the error and you separated it from high and low error, the low error physics that's happening at that scale. What you can do is just prove that the pre-smoothness, right, it's going to reduce the norm of this, or in the energy norm, or in the stiffness norm, by factor of p sub s greater than or much less than 1. Okay, and the coarse grid, it's going to be exact for low modes, okay? Because the coarse problem will capture them in the particular well that you choose. And then you can then, of course, use Galerkin. The Galerkin coarse operator will guarantee that correction is optimal in the energy norm of the projected problem. And remember how we define the energy norm. There's contingent variables that we use to define it, but it's essentially just encoding the bilinear, or it's encoding the weak form of the physics that we're trying to solve in general. So when in doubt, just think, what physical problem am I solving, and what does that relate to this kind of obscure mathematical idea? And then the last thing is the post smoothing, right? After we smooth it and clean up any remaining, frequency or high frequency pollution. So clean up high frequency pollution. I don't know if that's the right way to say it, but from the prolongation operator. So this comes from taking, we're at 2h, going down to h and interpolating, and then cleaning that up, right? The post-smoothing will help us then yield, a contraction factor that's bounded away from 1 and independent of h, and then you can prove the theorem. All right, so that's kind of what it looks like roughly. So the V, what do I mean by V cycles, right? I said per V cycle. Well, let me show you what a V cycle is. All right, I'm gonna just draw it out. It's not super hard to understand. So, say we have some initial guess, initial guess for our solution, and here's kind of the domain we chose is super fine. It's a fine grid. Let's say this is H here, and this will spit out some solution. Well, what we can do is perform the prolongation or really, sorry, the restriction, we're restricting to a coarser grid, if you will. Restricting, and these grids will look kind of like that, and until we get to the full H, and this is the lowest frequency. The lowest frequency would be solved exactly here, and what we can then do is perform the prolongation back up to get our solution. And so essentially what you do is you say high frequency damp smoothing, right? And then you go here, and then you damp the medium frequency smoothing, and then you'll do low frequency solved, and this is an exact solution. And then what you would do is prolong, smooth, prolong, correct, error correction, prolong, error correction, solution. Okay, hopefully that makes intuitive sense. That's why it's like this V, right? It's called a V cycle. And the V cycle doesn't, and also we proved again that the convergence, or what we should be able to get out of this is that the convergence is independent of the mesh size, right? The convergence is independent of the mesh size, and you can solve for like, order, this would be like order of n, complexity, where, you can choose, or n is literally, it would be, I guess n would be 1 over h here. It's I guess that's how you solve that. But yeah, the optimal complexity for n unknowns. Actually, wait, no, that's not true. I think, so this whole idea, right? This whole thing means that we can get, and plus the theorem. So for the V cycle, we can have mesh independent convergence rates, and so to reduce the error by a fixed factor of order 1 as h goes to 0, that's the first thing that's important to figure out, that one can have this. And so the total work then, the total work to have an optimal complexity for n unknowns would be of order n. Okay, so there we go. That's essentially everything that we have. So hopefully that makes sense, and I'm going to try to think about this a little bit more. And the physical intuition behind this is, for a coarse grid, right, the smooth error will be damped, and the correction interpolates the large scale. The correction will interpolate this large scale shape back to the fine grid. That's the most important part. So we do get a fine grid solution in the end. All right. Now, this unifies the energy norm, because what's happening is the multigrid is it's minimizing the same A norm error as the conjugate gradient. All right. So previously, when we talked about the conjugate gradient here, it is minimizing that same A norm error, right? This is the best possible approximation from the Krylov subspace, given a natural energy norm that's induced by A onto that particular projection scheme. But what's important here is we got an independent of H, right? It's like a hierarchical frequency decomposition instead of Krylov powers, all right? So this is just another thing to chew on, okay? I hope this is interesting to you, because I hope this is as interesting to you as it is to me, because this is really, important to recognize as another tool that you have, is the idea of what are the mesh independent things that I can do and take advantage of when it comes to, again, mirroring these Galerkin coarse operators that encode the correction energies to then interpolate back onto the grid. All right, so thank you for coming on this journey with me. And of course, remember, we're really trying to solve the same problems and, solve them more efficiently. But this one doesn't depend necessarily on the, quadratic energy landscape. But it's more so of a mesh kind of invariance that we found via some smoothing and applying different pieces of the previous episodes that we've had with the von Neumann analysis and the CFL condition, or the CFL stability, Courant numbers and everything, if you remember that. Well, what we're really doing is, we're just making this a variable instead, and some function that's just, manually deterministically smoothing out the harder frequencies. All right. So thank you guys for watching. I really appreciate the interaction with my videos, and let me know if you guys have questions. Let me know if you're enjoying this so far. And next episode we will talk about spectral graph theory. All right. Peace out.